So welcome to our seminar series in the Gemini Center on Quantum Computing. Our speaker today is Simen Kvaal. He has a PhD in physics from the University of Oslo from 2009, and he's now been a permanent researcher at the Department of Chemistry at the University of Oslo since 2014, which also coincides with an ERC starting grant in mathematical analysis of the bivariational principle. He does research in the intersection of mathematical physics, numerical analysis, and quantum chemistry. And he's very interested in the variational principle, or in variational principles in general. He studies and develops methods for the many-particle Schrödinger equation and related topics. Currently, he's leading a one-year project at the Center of Advanced Study at the Academy of Science and Letters, where he studies attosecond quantum dynamics without the Born-Oppenheimer approximation. Today, he will give a presentation on the multi-reference quantum chemistry problem on NISQ devices. So if you're ready, Simen, the floor is all yours.
Okay, thank you for the nice introduction. I'm going to give a presentation on a work in progress that I am doing together with Frans and Joachim. It is said that one shouldn't apologize in front of a talk because it just makes people feel embarrassed. But I will still apologize for not having had. I don't feel that I had the proper time to prepare this talk. But I hope that everyone can get something out of it. This is an outline of my talk. First, I will talk a little bit about quantum chemistry as it's currently done on the NISQ device. Then I will talk about the multi-reference problem, one of the greatest challenges in quantum chemistry. And then I will talk about the multi-reference unitary couple cluster method, which is a method that we propose. And then I will conclude. Wait a minute. Okay. So in a nutshell, quantum chemistry can be described as follows. We are interested in solving the electronic Schrödinger equation in the Born-Oppenheimer approximation. So this is an eigenvalue problem like this. And this eigenvalue problem has a parametric dependence on the molecular geometry. So if you look at this figure, it shows the caffeine molecule in a geometry which is close to what we call the equilibrium geometry. It has 24 atoms, and this is like a standard ball and stick model of this molecule. So 24 atoms in R, living in R3, means that it has a parametric dependence. This eigenvalue problem has this parametric dependence of this vector. So, and also this vector psi of R is an element of this Hilbert space, because we have 102 electrons in the molecule, and they all have spin 1/2. So it's like L2 over R306, and we have to take this number of copies of this space. So this is a very high dimensional problem. Now, from a functional analysis point of view, this Hamiltonian is very well behaved. It's a self-adjoint below bounded partial differential operator. We know a lot about it. But this is a very hard problem. So what shall we do? The standard approach to discretizing this problem is to use antisymmetric tensor products, or determinants, as quantum chemists say. So the antisymmetry of this wave function, the Pauli principle, is expressed in this form using quantum mechanics notation. So if we exchange two particles' coordinates, we obtain a minus sign. So this function is then discretized by taking antisymmetric tensor product. So we have a set of what we call single particle functions, 5p1 and 5p2, etc. And so this is an orthonormal set. And then we create a linear combination of the antisymmetrized tensor products like this. So we can see here that for these antisymmetric products to be linearly independent, we have to order their indices like this. This means that we can introduce what we call occupation numbers. So An antisymmetric tensor product can be identified with a string of zeros and one. In this string, we have a one in position P if one of these Pi's equals P. So there are in total n ones, and the rest are zeros. Okay. So part of what is called the Jordan-Wigner transformation is that the n-electron wave function with L single particle states, so L was the number of basis functions in this orthonormal set, it maps onto the state of an L-qubit quantum computer. I saw somehow that I skipped this slide. So, so if we look at a quantum computer, it has a single qubit has a state which can be described with this vector. If you have two qubits, we will take the tensor product of that space. So we will get like a 4-element linear combination. And if you have L qubits, we can write it in this form, with B1, B2, B3, etc. are zeros or ones. This is the exact same form as we had on the previous slide, which means that now we have a part of the Jordan-Wigner transformation. The n-electron wave function with n single particle states maps onto the state of an L-qubit quantum computer. So we already have like identification with a standard discretization of the Schrödinger equation with the state on the quantum computer. This is great. Now,
can I ask something?
Yes.
So going back to your very first slide, you don't have to go back, but are you saying that you're filling now basically atomic orbitals, right? That's the configurational space you work in. So the first remark, like I actually have all these degrees of freedom for the positions of these atoms, that's sort of gone now?
The positions of the atoms are gone. I now restrict myself to one fixed geometry.
Yeah, okay.
I should have said that, but we are interested. So we are solving the electronic Schrödinger equation for a fixed geometry. This is the Born-Oppenheimer approximation, roughly. So a motor behind many approximations in quantum mechanics is the Rayleigh-Ritz variational principle. So we have the Rayleigh coefficient, which we can compute the critical points of, and that will be the Schrödinger equation. In particular, since the Hamiltonian is below bounded, we can compute the smallest eigenvalue as the infimum of the Rayleigh coefficient, and this will always be bounded below an approximate ground state. And this approximate ground state is obtained by minimizing over a smaller subset of the Hilbert space. This is a standard method. So let's talk about single reference theory. So quantum chemists talk about single reference and multi-reference theory. So we usually start with the mean field approximation of typically the Hartree-Fock approximation, where the wave function is written as a single antisymmetric product. So we call this the Hartree-Fock function, and using the occupation number notation, this is the Hartree-Fock function. And Hartree-Fock is defined as the determinant that minimizes the total energy. So this is the variational method again. So we minimize over this, this manifold. This will actually give us a discrete basis, not only the first n functions needed for this function, but also auxiliary single particle functions. So I means the n first, and a means the rest of the functions corresponding to these positions. And we can now express the problem on the quantum computer in this basis using the Jordan-Wigner transformation, including the operators that we need to use. Now, corrections on top of the Hartree-Fock function are components that are orthogonal to the Hartree-Fock state. So we have the Hartree-Fock state plus a linear combination of something which is orthogonal. So this means that the binary string here cannot be this string. So whenever the correction of this difference here is small in some sense, it's always a little bit vague, we call psi a single reference wave function because it refers to a single reference approximation, if you like. Otherwise, we call it a multi-reference wave function if it's not possible to write it in this form with a small correction. So we'll come back to the multi-reference problem. Now, quantum chemists talk about excitations. It's sort of a physical phrase, but what it means. So we talk about excitations relative to the Hartree-Fock determinant. Excitations generate all the basis functions that we have, these antisymmetric tensor products. For example, if we take the Hartree-Fock function, so this bar here is just to divide between the n first and the remaining single particle states. A single excitations erases one of the bits here and inserts a bit higher up. A doubles excitation erases 2 bits. And a triples erases 3 bits, and so on. And for 4 particles, these are all the excitations we can create. So the singles, doubles, triples, and quadruples together build the whole many-particle basis set. So excitations are written using excitation operators. So we can define an operator xia, where I is smaller than n and a is greater than n. And this operator performs this bit manipulation. This is very simple, but it can be iterated so that we can create doubles by 2 singles, etc. And it's a fact that all these excitation operators commute. So the excitation operators generate a commutative nilpotent algebra of what we call cluster operators. For example, we have a singles operator here and a doubles operator, being linear combinations of the singles and the doubles primary excitation. For the n equals 4 case that we used previously, the full wave function can therefore be written on this form as the Hartree-Fock determinant plus all linear combinations of all determinants with 1 bit erased and then 2 bits erased, etc. And the Hamiltonian has a similar structure written in terms of something that looks like excitation operators, but we won't define this expression any further. It just serves to illustrate that everything is neatly formulated using, qubit states. And cluster operators are fun. They can be manipulated in various ways, and they sort of form the bread and butter for a quantum chemist. So the simplest correction on top of the Hartree-Fock approximation would be what we call configuration interaction. For example, Ci singles and doubles, CISD, is obtained by taking the Hartree-Fock determinant plus singles and doubles corrections. And then we minimize using the Rayleigh-Ritz principle. So this becomes an eigenvalue problem. This is sort of an intuitive starting point for improving the Hartree-Fock approximation. However, the exact E of R, this is the ground state as a function of the positions of all the nuclei. So we are now considering only one fixed R, but if we were to vary R and compute what we call an potential energy surface, it has a geometric property called size consistency. It is very important for a quantum chemist to provide accurate calculations. In particular, size consistency, which we won't have time to talk about, is a very important property. But the Ci approximation breaks its property. So we won't use Ci. What we will use? We will use Kappa cluster theory. And briefly speaking, Kappa cluster theory is obtained by taking the exponential of a cluster operator. It's really weird, but that's part of the fun of the cluster operators. This is a very natural thing to do. And the Schrödinger equation can be written on this form. So I simply take my, I call this sum of T1s, etc., as T. And we similarity transform the Schrödinger equation. And we now have a non-linear version of the Schrödinger equation. So it doesn't sound easier, but this now has size consistency built in because of the exponential operator. This is my magic. No, it's not magic, but yeah. So couple clusters, singles and doubles. Yeah.
Simen, could you maybe say something what the size consistency means? So I have no idea. Like.
Yeah. Okay. I can say what it means. Size consistency. So imagine we have a molecule consisting of. Okay, we have two molecules, a molecule here and a molecule here. They are far away from each other, so they do not really interact. The Hamiltonian has such a form that when the molecules are far apart, they will not interact. It's sort of natural. Now, if I use my method, numerical method, for example, CI, singles, doubles, and I apply it to my first molecule, then I apply it to my second molecule as separate systems. And then I apply it to my combined molecule. What will happen? Intuitively, since the systems do not interact, I should get the sum of the energies, right? So this system here and this system here has energy EA and EB, and the combined system has the sum of the energies. However, with the CI method, this is not the case, because you restrict yourself to singles and doubles excitations only, which means that if this system here is allowed to excite, then this one cannot be excited. The basis functions you use cannot simultaneously excite on both places. I mean, doubles here and doubles here. That is a quadruple, so this is not allowed. Now, in the couple cluster method, because we have the exponential, and since the exponents actually commute, we can have both a doubles excitation here and a doubles excitation here to produce a simultaneous excitation. So size consistency is roughly speaking the asymptotic behavior of the potential energy surface as you move fragments around. And this separation property is very important to reproduce experimental results. Was that somehow?
Yep, thank you. Yeah.
So I will just say that the standard couple cluster method is now a non-variational method. I won't go into details, but it's a non-variational method, but it is polynomially scaling on a classical computer. So this is very much preferred since it's size consistent. But a variational version of the couple cluster method is unitary couple cluster method. So this is obtained by acting with an exponential on the Hartree-Fock state, where this exponent is anti-Mitchell. So this is now a unitary transformation. And then we minimize using the Ritz principle. We minimize over all such sigma. For example, this T can be a singles and doubles, and then we minimize. Now, the UCC method has been considered academic because it is very expensive on the classical computer. However, in a seminal paper, Peruzzo and his co-workers, they realized that the quantum computer can prepare the UCC wave function in polynomial time. So the UCC parameterization is very natural on a quantum computer. But there are many open questions with the UCC parameterization. For example, we do not know if the UCC parameterization can reproduce the whole Hilbert space of n electrons. We don't know. So there are many interesting questions related to UCC, but it produces good results. So UCC is a poster child for quantum computing applications, and there's an enormous research activity currently to apply this. So the UCC method is the UCC energy is minimized using the variational quantum eigensolver, which has a quantum part and a classical part. So on the classical computer, we have an optimization of the energy function, and the energy function is evaluated on the quantum computer. So the quantum computer has a quantum circuit A that prepares the wave function ansatz, for example, the UCC ansatz, and a quantum circuit that evaluates the energy of the state stored on the quantum computer. So then we get a cycle like this. So we have parameters on the classical computer that maps to a wave function on the quantum computer. The energy on the quantum computer is output back to the classical computer, and then the cycle goes on. So the multi-reference problem, what is that? Well, there's a certain lag on my computer. Okay, the independent particle picture, the Hartree-Fock approximation, is often wrong. This is a big problem. Even for small molecules, as you will see, this picture breaks down. So the Hartree-Fock model is a one-body approximation where the total Hamiltonian is broken down into an unperturbed operator and a perturbation. So the Hartree-Fock wave function is an eigenfunction of this operator F with an energy EHF. And if we consider psi, the exact eigenvector, as a correction on the Hartree-Fock state, then we can consider this problem using perturbation theory. So we include some kind of scaling parameter G, and then we write the full wave function as a series. This is pretty standard. And the first order correction to the wave function is this well-known expression for people doing quantum mechanics. In particular, we have the resolvent operator here. So we see that if we have a large gap in the Fock operator, then sort of this perturbation can be considered small, because then the first order perturbation will be small. So Hartree-Fock is a good approximation. If the gap is small, then we get sort of get huge contributions here in this first order. And then we call it the quasi-degenerate case, because the Fock operator is almost degenerate. It has eigenvalues that are clustered together. And then the Hartree-Fock state alone is bad. Well, it's more complicated, but this is sort of the intuitive picture to keep in mind, that the Fock operator has this zero order approximation here, has the eigenvalues that close together. So here is an example. This is a slide created by my former postdoc and now colleague, Tilman Bodenstein, showing a very simple potential energy surface of insertion of a beryllium atom into a hydrogen molecule. So this atom moves into this molecule. And so this is a very complicated plot, but the take-home message here is that the coefficients of the Hartree-Fock approximation determinant, so they change rapidly as the atom is inserted. So here we have a very good, the state is very close to a single determinant. And here it is also very close to a single determinant as a function of the distance of this atom. But in this region, it's a very complicated behavior, just for a very simple molecule like this. So it's one of the greatest challenges we have in quantum chemistry, because we have no black box methods for such cases. It's a craft to solve such problems. So when the single reference wave function was written as a Hartree-Fock determinant plus a small correction, the multi-reference wave function is now written as something which is called a model state and a small correction. And the model state is the set of determinants, it's a subset of the determinants. So you sort of, instead of having all n electrons in the first slots here, you allow them to propagate a little bit further. So here we have n particles in an m equals 6 model space. So m is the number of single particle functions that you allow your electrons to live in the model space. So we generate then a number of determinants using this rule. Okay, and then you can take linear combinations of all these and get a good approximation to your state. This is the idea behind multi-reference methods. And now multi-reference UCC. So now we introduce a new variational principle. The variational principle for this, it's not my invention, but it's new in this context. The sum of the k first eigenvalues of the Hamiltonian can be obtained as follows. So we introduce an objective function g of p. And this is the trace of the Hamiltonian acting on p, where p is now an orthogonal projector onto a subspace of dimension k. If we minimize this function over all such projections, we will get the sum of the smallest k eigenvalues. And the critical point condition for this functional is often called the Bloch equation. The same Bloch as the Bloch waves, I think. This condition. And it means that this condition means that at the critical point, the projector is a projection onto the eigenfunctions in question. Okay, in particular, at the minimum is the projection onto this few first eigenfunctions. And the idea is that this variational principle is the proper setting for the quasi-degenerate case, multi-reference case. The assumption is that the model space resolves the quasi-degeneracy. So we write, now it's getting a little bit involved now, but we write the projector submanifold, we write down the projector submanifold with perturbations of the model space vectors. So this is the general projection operator, orthogonal projection operator. And we let our vectors be UCC vectors relative to n, where n is a model state. What does this mean? Well, if we note that n is a permutation of the Hartree-Fock bits. Go back. So these states are called, this is a state called n. And we see that I obtain it by a permutation of the bits. So this is now a unitary operation. And then I can write my psi n, which is defined as something like this, as a permutation of an exponential. And this is now a standard UCC operator. So this is a UCC wave function, and then I permute it. Right. And this sigma is now supposed to be this anti-Hermitian cluster operator. Yeah. So we now obtain the following objective function. So theta, my parameter space, is the set of cluster operators. There's one cluster operator for each model vector. And mu is just a generic index that counts the singles and doubles excitation. So this is a long vector that I have on my computer. And my objective function in terms of these parameters is the trace of the projector times Hamiltonian. So it's this expression again. And the multi-reference variational quantum eigensolver will now minimize this functional classically, evaluating this g theta on the quantum computer. That's the main idea. Can it be done? This is one of the questions that we are trying to resolve in our little group. What we need is to need to prepare the wave functions that compose the projection operator. So this is our UCC state, and it's a standard to prepare on the quantum computer. And then we need to permute it. And this should also be fairly standard. So this should be straightforward. And then we need a circuit to evaluate the matrix elements. So there should be a prime in this equation. We need to evaluate matrix elements of the Hamiltonian and inner product of wave functions, where psi and psi prime resides in different qubit sets. So the idea is that each of the UCC states is prepared in a qubit subregister. So we have L qubits for one function. And then we need to compute inner products of different subsets of qubits and also matrix elements of the Hamiltonian. It's slightly unclear how to do this. What would be sufficient is that if we had a circuit for computing linear combinations, we could use the polarization identity to extract inner products and matrix elements. So that's all. And I can conclude that we have seen how the electronic Schrödinger equation maps onto a quantum computer qubit register in a natural manner. And we have seen how unitary couple cluster theory is formulated. The multi-reference problem is a great challenge for quantum chemistry, and we want to solve it on the quantum computer. So we provide an outline of a multi-reference unitary couple cluster method based on a variational principle. So what we need to do is we can do benchmark calculations on a classical computer with this method, but we will also run simulations of this on a simulated quantum computer. But of course, it will be cool to have it on a proper quantum computer. So thanks to my partners in crime, Frans Fuchs and Joachim Berge.
Thank you very much. Are there any more questions?
I have a question, if it's okay.
Mm-hmm.
So it seems like you can get the multi-reference headache problem to become polynomially scaling. But with respect to sort of within a reasonable time span, let's say 10 years. So what's the sort of difficulties or crossover with respect to doing larger systems, like, for example, the caffeine molecule you showed, and with respect to having, I guess things get quite complicated on the quantum computer as when you have more qubits. So when can we expect that this sort of this development makes life easier for us in everyday life?
Yes, of course, there's a certain aspect of this method being of academic interest. On the other hand, okay, so the caffeine molecule is just for fun, and it was just displayed to show the scaling of the electronic structure problem. But on a serious note, if you want to solve the multi-reference problem on a quantum computer, what can you do? I mean, you will need to come up with, so the single reference unitary couple cluster method is variational, but it is still a single reference method. And if you want to handle multi-reference systems, I think that the best scaling is, so actually, what this method, so I presented this as if it needed like as many qubit subsets as there were model functions. But since you're only computing in the products of 2 at a time, you actually only need double sets of qubit registers if you can afford to create the states many times over, right? So you can work with pairs. So in principle, it's actually scaling quite well. But I mean, I have no idea how the optimization of this objective function will actually perform. I mean, I can imagine it's quite hard. And second, I mean, if you repeatedly create the states over and over, there will be some noise. So it's yeah. But so the time span, I don't know. Franz, do you have any? What do you think? When can we do, like, how many qubits can we do now? And could you provide, I mean, if we only need 2 qubit subsets could we do, for example, beryllium dihydride, which I showed an example of, it's only a 6-electron system. So, and even in a small basis, it's a challenging problem. So we could, I think it's reasonable that this could be implemented.
Can I shortly interrupt? I also had a question in this, exactly this. So how many qubits do you need for this? So what's the size of this? Because I don't understand how the beryllium atom, this example you showed.
So it's for small molecules, we have so I think we would need some order of to store a wave function for beryllium dihydride. We would need like Franz or Ida Maria, do you remember how many single particle basis functions do we have in this simple basis set, this double zeta basis set for the beryllium dihydride? I don't think it's many. So let me go back.
It's like 14 for beryllium and 5 or so for each hydrogen, right?
Yeah.
Yeah, I think so.
So 24 probably ish.
And you can probably freeze some in the core and do some simplifications with
So let me say it's on the order of 30. So since the basis set has the order of 30 elements, it's an order of 30 qubits that is needed for a single UCC wave function. So 60.
And how complicated is like the preparation? Like how you have this exponential operator that you wanted to apply to the wave function, right? I mean, what's the depth of this if you want to write this as a circuit? That would be another.
You're asking the questions that probably Franz can.
60 qubits we have, but I mean, right? But or the Google device has 60 or qubits, but already you cannot do many operations on it. So
no, I think that's one of the challenges, right? Because you need to, you have the exponential of this cluster operator, the T minus T dagger, and these will have to be compiled into Pauli strings. And then you can compile it down to gates. And the larger the system and the more of these terms you have, the larger the depth of the circuit will become. I don't know the exact scaling, but in principle, it's NISQ friendly. But you need not only the number of qubits, but also the decoherence time and the error level should be low enough.
But I mean, in the time frame of, let's say, 10 years, I would assume that there would have been some improvements. So, I mean, unless you come up with a completely new electronic Schacter method that handled multi-reference character with the same qubit that a single reference methods have today, I mean, then this is the best you can do. I think I think this type of method is the best you can do with like traditional multi-reference thinking.
Isn't sort of the takeaway message that you require the double amount of qubits, but the depth is the same as for a single reference?
Yeah, I think so. That's it, because the only modifier is that the standard UCC method on the quantum computer evaluates the energy of a single state. And this is not evaluated as an inner product. Right. So this is, so we need to sort of find a way that can be solved if we can prepare linear combinations.
I was a bit confused by this. So what do you mean by this? Like, so you want to evaluate the inner product with the Hamiltonian, or?
Yeah. So the expectation value is not implemented in the manner that you first have a state, you act with the Hamiltonian, and then compute the overlap with the state.
No, I mean it's a measurement, right?
Yes.
Yeah, but it's two different states. It's the inner product of phi1, phi2 with respect to the Hamiltonian.
Okay.
So
Yeah,
that's
this
much
is,
more challenging.
but if we note that if we could produce linear combinations, then you could compute psi1 plus psi2, and then measure its energy, and then psi1 minus psi2, and then measure its energy, and then you can use the polarization identity to extract. Yeah.
I think I've seen a paper that proves that this in general, for general states, phi1, phi2, this is not possible. But I will have to look it up one more time.
Yeah.
Can I just ask just one more follow-up question with respect to standard multi-reference methods? Because I think like even only if it's still at the purely academic interest, I think these things are very interesting since the multi-reference problem is really a problem. And I was wondering, it's like now I haven't seen the equation or the exact theory or the depths of it, but would there be a possibility that there are something to learn from doing multi-reference on quantum computers that makes us sort of be able to take a step outside of our standard approaches in standard electronic structure theory to make new multi-reference methods? Because I think I see that the way we do multi-reference today on traditional computers is, yeah, it's not really going anywhere.
Yeah, I see what you mean. And well, I think that there are some, the mathematics behind the multi-reference problem is a little bit complicated. And one of the reasons why the multi-reference problem is so hard is that it's difficult to come up with a general black box prescription for model spaces. This is one of the first problems. And the second problem is that the multi-reference couple cluster methods we have today, they are not so good, and they are typically not derived using variational principles. I mean, this using this sum of eigenvalues principle is something that leads to very complicated formulas, but when you have in the unitary couple cluster case, it's actually not so complicated. But if I'm not sure if the quantum computing paradigm can sort of give fundamental new multi-reference methods. I don't know. It's a little bit hard to. Yeah, I mean, surely this method cannot be used. I mean, we won't get quantum supremacy for this method. Not yet, at least.
Can you use tensor network methods for these kind of problems? Or
Pardon?
Can you use tensor network methods or like MPS for these kind of problems? These multi-reference.
I've been thinking whether or not there would be. I mean, the tensor network methods, they are polynomial scaling already, and I mean, I'm not sure if there could be some.
I mean, it's a classical method, so not a,
Yeah, I mean, I have been speculating whether one could use if there could be some kind of what do you say? I mean, the steps you do to introduce the matrix product state or the DMRG algorithm is sort of motivated by classical constraints in a way. So if one could instead consider what constraints do we have for a quantum computer and find it a way for it to sort of to produce in an efficient manner, maximally entangled states in a way. I know, but it's a good question whether one could sort of use matrix product states in a way in such connection. It's very natural, certainly, because it's, I mean, it's, yeah. Because the quantum computer state is naturally formulated as an element in Fock space. It's a very
Can I maybe ask like one final small question for the quantum chemist? So you're saying that this beryllium H2 this would be like a system where you don't understand like really what's happening in this particular point.
This is, I mean, this problem is so much studied that, I mean, we know a lot about the system.
Okay.
But it's a very good, it's a standard test bench for novel multi-reference method, because it has a very complicated behavior for such a small system. And a good multi-reference method should be able to resolve all that complicated features in an efficient manner.
Okay.
We can solve it, yeah.
So what would be the simplest system that you cannot solve using classical methods?
I don't know.
Really like the...
You know, Ida Maria, do you know?
So I don't know, I guess it depends on a little bit on the basis that you use, right? With a minimal basis, you can go larger. So it depends on your, like the balance between the right n-electron function, wave function, and the right one electron basis set, which in the end will give you how good is the result. So there's a sliding, it's a sliding door. It's not an exact step, I think.
No, but like, so I don't know, if like in 100 years we have a quantum computer or something, right? So what would you hope, like, is there like a concrete problem where you say that like maybe your quantum chemistry methods don't agree with the experiment and you don't, where the quantum computer could help? Like, so I mean, I'm working in quantum information theory and quantum computing, like a bit, and it's always like the question, what would be like the simplest case where the quantum computer could contribute to something where some more classical methods fail? And I have not heard like a clear answer to this. So there's always this fertilizer problem that always somehow pops up there, but I don't know.
Well, basically any type of chemistry which involves breaking and the creation of bonds is a problem, right?
Okay.
So with respect to changing at least the geometry, but then there's for just a given geometry, the multi-reference problem. I mean, whenever you have transition metals, it's usually can be problems. And I don't know about Simen, if you have some small example.
It would have to be a system which is sufficiently large so that we cannot go to chemical accuracy with the methods we have, but sufficiently small that we can do something with it, because we cannot, I mean, the system that we could treat on the quantum computer would be, with the methods we have, would be reachable with some standard. I mean, what I'm trying to say is that on the quantum computer, it's difficult to visualize a system which is such, I mean, that the quantum computer can do something which a system which is so large that we cannot do anything classically. It doesn't make sense, because the storage requirement of, I mean, you can always use Hartree-Fock, and you can use simple corrections on top of that. And the quantum computer should then, okay, so the system should be sufficiently large so we cannot go to an accurate multi-reference description. which means that we cannot get chemical accuracy. So that's, but this question needs careful consideration because it's very important to identify the sort of the tipping point for quantum supremacy. There are some papers on multi-reference quantum chemistry on quantum computers already. Maybe these papers can offer some clue. I don't know.
Okay, thank you very much. I think we should conclude. Thank you very much, Simen.